Okay, so let's just look at your pie chart. So we had this disc up here at the top, and here is the incline. And then later, your disc was rolling and down here. So there's my dotty dot dot where it's going to be in the future. It was rolling and it was moving. So you drew this pie chart where all the energy in the system must be conserved, so the pie circles are the same. So this is my pie chart for snapshot 1, and this would be snapshot 2. So then down here, or down at the bottom, you're right. It is all kinetic energy. But there's now a subgroup. We're going to split kinetic energy into its pieces. So instead of just all kinetic energy like you have thought about previously, this is like some kinetic energy is translational. That's a KT there. And then maybe some of it, another portion of it, is, and I'm going to draw it over here because I'm out of space, but EK rotational. So rotational energy and translational energy. The object is translating and it's rotating. So this is translational. Kinetic energy. And oh, and this should have been an R. And this is rotational. So my rotational kinetic energy. We're going to put all this together in just a minute, but before we do that, we have to really look at the motion of something that is moving in a circle. And so what I want to do is look at an object that's only translating. So imagine we covered this disc with a super slippery goop, and we covered the track with a super slippery goop. So like made it into a slip and slide. Do you roll on a slip and slide? You just slip on a slip and slide. Okay. So every piece of the disc would be moving with the same velocity. So the piece down here would be moving with the same velocity as a piece of the disc up at the top, or as a piece of the disc down here. All of them would have the same velocity, which I'm going to call VCM for center of mass. So the center of the object is moving at the same speed as all the other pieces. Every single one of them. Even if you look at this piece right here, this piece right here, this piece right here, any of those little pieces of that mass would all have the same velocity. Just translating. Now with rotation, so imagine a bicycle wheel or a disc that has an axle, and all you do is give it a spin and it spins around and around and around. It's not moving left or right. It's not moving up and down. You give it a spin and it just spins round and round in a circle. So this thing is spinning and it has that angular speed. That was the omega, the angular speed. I'll take my little blue pen over here. And if you remember, it was in radians per second, so it even looked like a speed. Okay? And so on that disc or hoop or whatever this circle is that's moving around and around, every little bit of the edge has a tangential velocity, just like when we were studying circular motion. And every piece is moving tangent to the circle. So if you were to just watch a piece of the bicycle tire or the rotating disc, it's all moving around the circle all has this velocity v. Just going to leave it at v. So this is what rotation looks like. So then when this thing rotates and goes down the incline, it's doing both of these things at the same time. So we're going to put these two translation and rotation pictures together. So imagine taking them and superimposing those circles on each other with VCM and the V's together. Now, in order for it to rotate, it does not slip. So what is the velocity, the net velocity of the contact point between the disc and the ramp? So if it's not going to slip, so this point right here does not slip. But this point right here has a velocity, according to the translation, that would be equal to the V center of mass. And you know what? I'll put some subscripts up here just so we can keep it cleanish. This will be V. We'll call these all V2s. Okay? And down here, this piece of the wheel, remember we're putting them together, this piece of the wheel will also have a velocity of V2 backwards. And if it's not going to slip, but it's going to grip the road, what is the speed of that point on the circle? It's 0. So, what does that tell us? That V2 must be equal to VCM. Because the net velocity is 0. So that point's not moving, which is kind of fun. The center of mass doesn't have a rotational or a tangential velocity because it's the center, r is 0. So it's still just moving along here at V center of mass. Now what about the top? At the top it has a velocity that's equal to the V center of mass, but also didn't it have a V sub 2? So what is the result of the speed of the piece of the mass up here at the very top? Oh my gosh, it's moving twice as fast as the center, right? So this would be equal to 2 times the velocity at the center of mass. So as you watch something roll, the point on the circle that's in contact with the ramp is actually not moving. It's still for the instant that it's touching. And the piece that's furthest away from the ramp is moving the fastest at that instant. And if V is equal to r omega, where r is the distance, omega was the angular speed, then we could find the speed of the center of mass, which will let us find the speed of a particle at the edge of the circle, if we needed to, the top edge of the circle. So the next fun ride for an amusement park would be some sort of barrel that you roll down an incline in because you're going the fastest at the top, but you stop momentarily at the bottom. So you have all these changing velocities and speeds, and would be lots of fun if you roll down a hill before. Okay, so we're going to still use this idea that every little piece is moving around here. And let's go back and look at our energy. So we had E gravitational converted to, transferred to, remember energy, think of energy as being stored. So we have energy stored in the gravitational field between the disk and the earth. And then we have energy stored in its motion, but it's got two kinds of motion now. It's got motion translating and motion or kinetic with rotation. So this takes care of the fact that the whole thing goes from the top of the ramp to the bottom of the ramp. The rotational portion takes care of how much energy does it take to get that thing to roll. So if E sub G is mgy, and kinetic energy of the whole thing would be 1/2 mv squared, and that would be the velocity of the center of mass. Okay. Then I want to kind of look at this rotational kinetic energy as if we've got this disk. And this disk has a bit of mass right here. And that bit of mass, actually, I'm going to back up one step. Instead of a disk, we'll look at a hoop, like a hula hoop. So this bit of mass right here on the hoop is moving this way. Does that little bit of mass have a velocity? Yeah. So the whole thing has to rotate. Now, its velocity is going to depend on the distance and its angular speed, because V is equal to R omega. So if kinetic energy is 1/2 mv squared, but this is, I don't need the translational velocity, I need the speed that describes it going around and around in a circle. So instead of V, I'm going to use R omega squared. So then that gives us this mgy is equal to 1/2 mv squared plus, now this new thing here, this will be what? 1/2 mr squared omega squared. Now check this out. Kinetic energy has a 1/2, a mass, and a speed squared. This rotational energy has 1/2. It has a mass, but what did you find about the position of the mass? Did the position of the mass change how it rotated? When they were all four close to the center versus all four of them far from the center? So I bet that M is going to have this R dependency. And so maybe instead of it just being just the mass of the disk, but maybe it's how that mass is distributed, where it's located. And then this right here looks like my speed. So what is this thing right here? This mr squared. This tells me how the mass is distributed. This is called the moment of inertia. Yeah. You cannot use that if the mass is unevenly distributed. In order to find the moment of inertia, you have to take the integral of r squared dm. So we are going to use nice symmetrical shapes like disks, spheres, hoops, cylinders, where the moment of inertia is much, much easier to define.